Okay, our lesson today is to be or not to be a function. So first thing I want to do is I want to look at several different functions that are very, very important in the math classes. Our first function that I want to talk about is the linear function. And do any of you know what that word linear means? Linear means line. So the linear function's graph is going to be a line. So I'm going to write that down for us. The graph is a line. That's what the word linear means. And you can see the word line within the word linear. So a linear function is always a line. And I'm actually going to draw for you the parent. And the parent's equation is y equals x. And we're going to talk about this a lot more throughout the year. And then I'm going to show you a fancy way of writing this, which is f of x equals x. That is the same thing as y equals x, but y and f of x are just different ways of representing the same information. And we'll talk about this more later. So let's go ahead and graph our linear parent function, which has an equation of y equals x. So it goes through the origin, 0, 0, and then the slope is 1, and we'll talk about slope later in the year, but that means the graph goes up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, etc. And then I can connect these dots with one straight line, and that is an example of a linear function. And in particular, this happens to be the linear parent function. So its equation is y equals x, or f of x equals x, just to get that on the picture. Okay, the next function I want to talk about is the quadratic function. And I'm going to make this a capital U and spell the word quadratic this way. So let's talk about the quadratic function. I used a capital U when I wrote quadratic because this graph is a U-shaped graph called a parabola. So let's write that down. The graph is a parabola, which is a U-shaped graph. So I wrote quadratic using this capital U, hoping that that would remind you that the quadratic graph is a U-shaped graph. And it's also called a parabola. That's its technical name. Now, I want to show you the equation for the parent function for our quadratic, and that is y equals x squared. And the fancy way of writing that is f of x equals x squared. Okay, I want to show you what this looks like. Its vertex is at 0, 0. And then I'm just going to plot a couple points, and then we're going to connect them. And later in the year, we'll talk about why the graph looks this way. So I'm actually going to go up 1 and right 1, and I'm going to go back to my vertex, and I'm going to go up 1 and left 1. The next thing I want to do is go to my vertex and go up 4 and right 2. I'm going to go back to my vertex and go up 4 and left 2. And like I said, I'll explain this later in the year. So why the graph actually looks this way. And then I try to connect it with a nice smooth curve because I want it to look like a U. Okay, this is our quadratic function, and it happens to be our quadratic parent. And so its equation is y equals x squared, or f of x equals x squared. Okay. The next function I want to show you that's very important in a math class is our absolute value function. Our absolute value function, it takes a V shape. This graph is V-shaped. So let's write that down. Graph is V-shaped. And the name kind of helps us remember that. Absolute value has a V, and so the graph is V-shaped. Okay, let's write down the equation for the parent to the absolute value functions. And the parent equation is y equals absolute value of x. These two straight up and down bars are absolute value bars. And that is our equation to our parent function. And then the fancy way of writing that is f of x equals the absolute value of x. So let's go ahead and draw a picture of this. It also has a vertex at 0, 0, just like the quadratic function, and it has a slope of 1. So it goes up 1, right 1, up 1, right 1, up 1, right 1, kind of like our linear parent function did. But because it's a V, I'm going to go the other way too. So I come back to my vertex here, and I'm going to go up 1, left 1, up 1, left 1, up 1, left 1. And then I can connect all my points with two straight rays, and this makes our V shape. This is our absolute value parent function. And just to write its equation down again, it's y equals the absolute value of x, or that could be written f of x equals the absolute value of x. Okay, and the last parent function we're going to talk about today is our exponential parent function. And I don't have any tricks to remember this. So I'm just going to draw the picture and show you what it looks like, and then I'll come back and I'll write down its equation. So it's up here at the point 0, 1, and then it comes really, really close to hitting the x-axis, but it's never supposed to get there. I know it looks like I bumped into it, but it comes really close to touching the x-axis, and it never gets there. And then it goes really high up, 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 real, real fast. This is our parent exponential function. This is like if, say, you went home and your mom gave you a penny one day, and then the next day she doubled the amount of pennies you had, so you had 2 pennies. The next day she doubled that amount, so you had 4 pennies. Then she doubled that amount the next day and you got 8 pennies. That amount of pennies that you have over time just grows really, really fast, which is called exponential growth. Okay, let's talk about the equation for this. And our parent equation is y equals a to the x. So just to show you an example of what it might look like, you might see something like y equals 5 to the x. And this is something that we're going to talk much more about later in the year. So let's just look at these. We have our linear function. Linear means line, so the linear function is a straight line, and this happens to be our linear parent function, which has the equation of y equals x. Our quadratic function, think of the u in quadratic. This is our u-shaped graph called a parabola, so this is our quadratic parent, and its equation is y equals x squared. So any u-shaped graph is considered to be quadratic. Any one straight line is linear. This is our absolute value graph. Think of that V in the word value. The absolute value graph is V-shaped, and this happens to be the absolute value parent with the equation of y equals absolute value of x. And then if you have a graph that looks like this one, it comes real close to touching the x-axis and shoots up, That is called an exponential function, and this happens to be the exponential parent. Okay, so let's talk about what makes something a function. These pictures are all functions, and I'm going to talk about why they're all functions here in just a little bit. So, definition of a function. A function is a relation, which means a set of all kinds of ordered pairs in which none of the x's repeat. A function is a relation in which none of the x's repeat. All of the x's are different. And I'm going to show you a couple examples of what I mean and try to make that make sense. So a function is a relation in which none of the x's repeat. All of the x's are different. So let me show you an example of a function. We could have the ordered pairs 1, 3, 2, 3, and let's say 3, 5. This is an example of something that is a function. So let's just look for a second. Are x's different? Yes. If all the x's are different, then that's when I know that we have an example of a function. So think about going to McDonald's. You know how you have the dollar menu and you can buy all kinds of things for $1? You can buy French fries for $1, a Coke for $1, a McChicken sandwich for $1. So let's think of that in terms of McDonald's. Let's say someone ordered a number 1 meal and it cost them $3. And then someone else ordered a number 2 meal and it cost them $3. And then someone else ordered a number 3 meal and it cost them $5. That's all okay. That all works in real life. It's possible to have the... Okay. You can just set them down. Okay, thank you. So it's possible for, more than one item to cost the same amount of money, like on the dollar menu. So the number 1 meal may cost $3, and the number 2 meal may cost $3, and that's perfectly fine. There's nothing wrong with that. So this is an example of a function. As long as the x's are different, as long as these x's don't repeat, you should be okay. It's okay that the y's are the same. That doesn't matter. Let me show you an example of something that's not a function. We might have the point 1, 3. We might have the point 2, 3. And we might have the point 2, 5. And let's think of this in terms of McDonald's also. So someone orders a number 1 meal and it costs them $3. Someone else orders a number 2 meal and it costs them $3. And someone else orders a number 2 meal and it costs them $5. So think about you and your friend going. You order a number 2 and it costs $3. Your friend orders a number 2 and it costs them $5. You got the same meal, but it cost one person $3, the other person $5. That's not right. That's not fair. And McDonald's will go out of business if they charge people different prices for the same thing. So this is an example of something that's not a function. And you can see the x's repeat. If the x's repeat, then that is an example of something that is not a function. Because you can't have the same meal costing different amounts of money. So this is an example of something that's not a function. So basically look at the x's. If x's repeat, not a function. If the x's don't repeat, then it is a function. Okay, we have another way to figure out if something is a function or not. And that is called the vertical line test. The vertical line test is a test that you can perform on a graph to determine if the graph represents a function. The way it works, A graph represents a function if all vertical lines drawn through the graph intersect the graph at exactly one point. So if you draw vertical lines and they only cross the graph one time, then it is a function. So let me show you some pictures of some functions. We might have our linear parent function that we spoke about just a second ago. The linear parent function looks something like this. This is an example of a function because no matter what vertical line I draw, I only touch my graph once. Touched it once, touched it once, touched it once, touched it once. That's an example of something that's a function. Another example was our quadratic parent. Quadratic means it's U-shaped, it's a parabola. This is an example that is a function. If I draw a vertical line, I touch my purple graph once. Touch it once, touch it once. If vertical lines can be drawn and you only touch the graph once, then it's a function. Let me show you the absolute value parent function. The absolute value is a V-shaped graph. And if I try to draw vertical lines, I only touch the graph once, touch the graph once, touch the graph once, touch the graph once. Those are examples of functions. Now let me show you something that's not a function. Let's say we have a picture that looks something like this. This is an absolute value function, but it is not. It's absolute value, but it is not a function because if I draw a vertical line right here, I cross my graph more than once. I touch it here and I touch it here. So if a vertical line crosses the graph more than once, then it is not a function. So that's our vertical line test. If you can draw vertical lines and cross the graph only once, it's a function. And if you can draw a vertical line anywhere and it crosses more than once, it's not a function. So let's look at these three problems and determine if they are functions or not. What do you think about number one? It is a function. This vertical line only crossed the line once. Only crossed it once. Only crossed it once. Only crossed it once. No matter what vertical line I draw, I only cross this line one time. So this is an example of a function. Now, if I wanted to know what kind of graph this was, I want to know, is it linear, is it quadratic, is it absolute value, or is it exponential? What would you tell me? And the answer is linear because it's a line. And linear means line. Let's look at number two and decide if it's a function. What do you think about number two? Do you think it is a function? It is not. If I draw a vertical line right here, I cross that graph more than once. If I draw a vertical line here, I cross the graph more than once here. So this is not a function. And if I wanted to know what kind of graph this was, is it linear? Is it absolute value? Is it quadratic? Is it exponential? What would you tell me? And it is quadratic because it is a U-shaped graph. Okay, let's look at number three. What would you tell me about this? Is this a function? It is. This vertical line only crosses my graph once. This vertical line only crosses my graph once. Only crosses my graph once. Only crosses my graph once. So this is an example of something that is a function. Now, if I wanted to know what kind of graph it was, is it linear? Is it quadratic? Is it absolute value? Or is it exponential? What would you say? This one is absolute value because it is a V-shaped graph. So this is our absolute value graph. It's not the parent, but it is an absolute value graph. It just doesn't happen to be a function. Okay, next class I want to try to come back and try to write a summary, and then I also want to try to come and maybe ask some questions that we can use to try to study from. So the vertical line test, very easy to use. If a vertical line crosses the graph more than once, it's a function. If the vertical line doesn't cross more than once, it's not a function. And as far as just looking at ordered pairs are concerned, If you ever see an x repeat, then it will not be a function. And if the x's don't repeat, it will be a function. Think about that McDonald's example. You can't have two people order the same thing and get charged different prices. No way, Jose. Thank you.